In this video, we're going to have a look at how trig identities as well as compound angle formulas and double angle formulas can make it so that the left hand side of this equation can match the right hand side of the equation. So first of all, how I'd recommend you approach this is realizing that on the right hand side, everything is in terms of cos and sine. So we need to transform cot and tan in terms of cos and sine. Not only that, but all the angles involve theta and not 2 theta. So let's start by getting rid of 2 theta. Well, to find sine squared 2 theta, let's first find sine of 2 theta. We can separate 2 theta into theta plus theta, and that helps us use this compound angle formula. So we get that sine theta cos theta, because A is theta and B is theta as well. So sine theta cos theta plus sine theta cos theta again. So because these are like terms, we can just say that they add together to give you 2 sine theta cos theta. So let's do that. In that case, sine squared of 2 theta, you can replace that by squaring everything on the right hand side of the equation. So 2 squared is 4, sine theta all squared is sine squared theta, and lastly cos theta all squared is cos squared theta. Moving on, cot squared minus tan squared. How can we replace that in terms of sine and cos? Well, to start with, tan theta itself, I'm sure you know that that's equal to sine theta over cos theta. Using that, you can square everything, and you can say tan squared theta is equal to sine squared over cos squared. Interpreting cot squared, I'm sure you've heard that it's 1 over tan squared if you've gone through the topic of cot, sec and cosec. Sorry, I got a little bit lost there. And in that case, cot squared would be 1 over tan squared. So it's a reciprocal of tan squared, meaning it's just cos squared over sine squared theta. Let's now combine everything that we've sort of established into one whole equation in terms of sine and cos. So sine squared 2 theta, let's replace that with 4 sine squared theta cos squared theta. And then you put a big bracket around it. You replace cot squared with cos squared over sine squared. So cos squared theta over sine squared theta. And you subtract from it tan squared theta, which is sine squared over cos squared. Okay, now that we've got this far, how do we make it match the right hand side of the equation? Well, first of all, what do we know about subtracting fractions? We know we can use the smile and cross method. You can say that this is equal to cos squared times cos squared, take away sine squared times sine squared, all over sine squared cos squared. So let's do that. I'm going to do that just a little underneath. So we keep this as it is for now, 4 sine squared theta cos squared theta. So the trick with these is just try and experiment new things, keep going and keep trying new methods, and you'll see if one method sort of pulls through. But throughout the whole equation, bear in mind I'm keeping everything in terms of sine and cos, so it should work. Cos squared times cos squared is cos to the power of 4 theta. Take away sine squared times sine squared is sine to the power of 4 theta. All divided by sine squared times cos squared. So sine squared theta, cos squared theta. Now this almost matches what we have, isn't it? But the thing is, these sine squared cos squared thetas are in the way, and actually you can cancel them out because there's one in the numerator and there's one in the denominator. So that actually leaves you with 4, and then in brackets cos to the power of 4 theta minus sine to the power of 4 theta, which is why it's actually equal to everything on the right hand side of that equation. Quite difficult to come to, and there's multiple ways of getting to that answer, but I just showed you one way. Let's now go into using the right hand side of that equation to show that it can also be written as 4 cos 2 theta. And so cos 2 theta, using the double angle formula, that cos of A plus B is cos A cos B. I'm just going to put my wobble on the floor, it's making a little bit of noise. Minus sine A sine B. And also the fact that cos 2 theta, you can split it up into cos of theta plus theta. We get that as cos theta, which is cos squared theta, because both A and B are theta. Take away sine squared theta. Now what's the use in writing out cos 2 theta? It sort of gives you an idea of what you want to get to. So by the way, we're multiplying it by 4. So it's 4 cos squared theta minus 4 sine squared theta, meaning we somehow want to show that this whole thing here equals this, because then we can say it's also equal to 4 cos 2 theta. So is there anything you can spot here? Because there's already a factor of 4 here, but how does cos to the 4 theta minus sine to the 4 theta equal cos squared theta minus sine squared theta? Well, the trick to this is the difference of two squares. You can rewrite this whole expression out as 4 and then brackets cos squared theta plus sine squared theta, all multiplied. Oops, that kind of looks like sine 2 theta. All multiplied by cos squared theta minus sine squared theta. Yeah, because the difference of two squares works here. Now cos squared plus sine squared is just equal to 1. 4 times 1 times cos squared minus sine squared gives you 4 cos squared theta minus sine squared theta, which then equals 4 cos 2 theta. So yeah, the key there was using the difference of two squares. Let's now move on to this last part of the question. So, sorry, everything's getting a little bit messy, which is why I'm just getting rid of a few things. Okay, last part of the question. It says hence means you want to use what you've done beforehand in this part of the question. Solve that this all, which can be represented as 4 cos 2 theta in its simplest form, equals 2. And you want to find all the values of theta between 0 and 360. So let's start by making 4 cos 2 theta equal 2. Before we solve this, we have to change the domain because this currently is a domain for theta, whereas what we have is 2 theta. Let's multiply every part of the inequality by 2. 0 times 2 is 0. Theta times 2 is 2 theta. 360 times 2 is 720. Let's rearrange for 2 theta. So you divide both sides by 4 and you get cos of 2 theta equals a half. 2 theta then is equal to cos minus 1 of a half, which when you put that into a calculator, by the way, it gets your value of 30 degrees. Let's think of all the times that this repeats in between this domain. I'd recommend some students use the cast diagram, but I think the cos graph is the easiest. I'll show you why. Sorry, I'm horrible at drawing. Okay. With the cos graph, by the way, I drew it between 0 and 720 because that's the domain for 2 theta. We know that it crosses at 30. Let's say that's somewhere like here. When else will it cross? Well, if I just get a straight line tool, if we draw a straight line, we see that there's actually 3 more points of intersection. So there's 4 in total within this domain. How do we find those? Well, we find them using the fact that the cos graph is reflective. So like this value here is, because this is 30 to the right of 0, this here is 30 to the left of 360. So this value here is 330. How do we find the next values? Well, we know that cos values in general, they repeat every 360. So when you add 360 to this, that's when you get this value. 360 plus 30 is 390. And lastly, if we add 360 to the second value that we got 330, then we get 690 degrees. So those are all the values of 2 theta that fall within this domain. But what we ultimately want is values of theta, so we now divide everything by 2. 2 theta divided by 2 is just theta. 30 divided by 2 is 15. 330 divided by 2 is 115. 390 divided by 2 is 145. Is it? No, it isn't. Sorry. It's... Hold on. I'm very sorry. My mind has gone blank. 330 divided by 2. Wow. 165. 390 divided by 2 now is 195. And lastly, 690 divided by 2 is 345. And those are all your solutions of theta that fall in between 0 and 360. Hopefully that all makes sense. Again, a very difficult question, but I thought I wanted to go through it. And I think I have a playlist full of more A-star level questions in the description, so be sure to reach out and have a look at that. And be sure to like if this video helped and subscribe. It'll mean a lot. Thanks for watching.